Section 12.1, Internal Energy and Work in Gas Processes. How do we calculate the total thermal energy of a gas? Thermal energy from here on out is going to be related to the amount of heat transferred in or out of the system. Well, the total thermal energy, here we should actually define it or redefine it as internal energy so as not to create a confusion. And internal energy can be found by taking 3/2 times N times R times T. Internal energy is measured in joules. N is the number of moles. R is the gas constant at 8.31 joules per mole Kelvin, and T is the temperature in Kelvin. And it is caused by the random motion of these molecules. The book says internal energy is a state function. What does this mean? What are other state functions of a gas? A state function is a property of the system that describes that state at a particular time. The state functions depend only on the state of the system, not the path used to get to that other state. State functions could include density, enthalpy, entropy. Work is found on a gas by taking the pressure times the change in volume of the gas. It's also found as the area under the curve of a PV diagram. Now, if the work on a gas is negative P delta V, primarily by a negative change in volume, then work done by the gas would be a positive P delta V. Explain why work is not a state function. Well, work is not a state function because work is equal to force times distance, and distance depends on the path that you move, that you use to go from the initial to the final state. Since work is distance dependent and path dependent, it is therefore not a state function. Explain the difference between these two sentences. Work done on a gas, work done by a gas. Well, as stated earlier, work done on a gas results from a negative change in volume and is negative P delta V. Work done by a gas is work done to expand the volume, right, and is positive P delta V. Section 12.2, 2 ways to change the energy of a system. Review the work energy theorem principle in Chapter 6 on page 193 of College Physics by Edkina. Then read Experiment Table 12.1 in Section 12.2 in college textbook by Edkina. Then write a brief paragraph explaining why the work energy principle fails to describe each of these situations. The work energy principle states that the work is equal to a change in energy. That's primarily what it means. In experiment 1, the gas is in a fixed volume and it's heated. Since the volume is fixed, the work is 0. Well, because the temperature was increased, the internal energy increased. But if the work is 0, the change in energy should be 0. However, the change in energy, which in this case is internal energy, is also increasing and cannot be 0. So, for experiment 1, the internal energy increased because the temperature increased. The work was 0 because it was a confined volume, constant volume. Since work equals a change in energy, 0 there should be no change in internal energy. However, the change in internal energy was positive, so our results are inconsistent with work energy theorem. In experiment 2, the gas heated to a volume to expand. The temperature increased and increases the internal energy. The piston pushes down on the gas in the opposite direction of expansion, thus resulting in negative work on the gas. Let's take a closer look at what happened in experiment 2. In experiment 2, as the potential energy, the internal energy rather, U is going to increase as the temperature increases. So U should be positive. The delta U should be positive. The work on the gas is negative because we have compressed it, decreasing the volume. Well, work is equal to a change in energy. Now, negative work does not equal a positive change in energy. We have a positive change in energy here, and we have negative work done on the system there. That is also inconsistent with work energy theorem. Explain what heating means in terms of a process of transferring energy. Heating is one way to transfer energy from one object at one temperature to another object at a different temperature. Section 12.3, First Law of Thermodynamics. State the first law of thermodynamics. Well, work on a gas plus the heat are equal to the change in the internal energy. And this can be written in two ways. The change in internal energy can be equal to Q plus the work done on a gas, and I would say this is a case for the compression of a gas. And delta U equals Q plus a negative work by, because negative work by is the same as positive work on, and that would give you Q minus the work done by the gas. This would be more for the case of an expansion of a gas's volume. Read experiment table 12.3. Explain how the energy is accounted for in terms of the first law of thermodynamics. Well, experiment 1, what do we have? We have an increase in temperature, therefore delta U is positive. We have, remember experiment 1 was in a confined volume, so the work was 0, but we added heat to the system. So now it starts to make sense. Before, we had work equaling 0 equaling a positive increase in internal energy. That was not consistent with work energy theorem. But now we can see that if we add heat to the system, the increased heat added to the system does match the increased internal energy by the system. In experiment 2, we had the compression of the gas. Therefore, we had negative work done. The temperature was getting bigger, so the internal energy was getting bigger. Okay, and we had a situation where the negative work done on the gas didn't seem to match the positive increase in internal energy. But if we add heat, what's going on is there's more energy gained by heating than lost by working the gas, by compressing the gas. And that's consistent with an increase of that. So there's more of this and less of this to have an overall increase in internal energy. What does temperature measure, and what does it or does it not depend on? Temperature measures the average random kinetic energy of individual particles that make up an object. Temperature does not depend on the number of particles in the object. What does thermal energy measure? What does it depend on? Thermal energy measures the random kinetic energy of particles. Adding more particles at the same temperature increases the thermal energy of the system. What is the process of heating, and what does heating require? Heating quantifies the process through which the same amount of thermal energy is transferred between the system and the environment when they are at different temperatures. That is the key. So, which is at a higher temperature? A large iceberg or a 1 kilogram block of iron that is glowing red? Well, obviously the block of iron is at a greater temperature because the amount doesn't matter. which has a greater thermal energy? Well, even though the iceberg is at a lower temperature, because it has a significantly greater mass than the iron, it is going to have a greater amount of thermal energy. If the red-hot iron is placed on the iceberg, which direction will the thermal energy flow? Well, the transfer of energy always moves from the hotter object to the colder object. So in this case, it will flow from the block of iron to the iceberg. However, that is going to be short-lived because there is not a whole lot of mass for that block of iron. Read example 12.2, using the first law of thermodynamics, explains why it requires more energy to heat a gas at a constant volume than to heat a gas at constant pressure. Okay, let's take a look. At a constant volume, using the first law of thermodynamics, we can see that delta U equals Q minus the work done by a gas. But at a constant volume, work goes away because work is pressure times the change in volume. Therefore, the change in internal energy is equal to the amount of heat added. In the case of a constant pressure, what we know there is that delta U, the change in internal energy, is equal to the Q added minus the work done by the gas. When you add the work to the internal energy, we can see that heating a gas at constant pressure, well, you've got more going on there. It's not just because you have work done by the gas, you're not having to expend as much energy by heating as you would because you have some done by the work. So when the gas is hitting at a constant volume, right, the no work was done. Again, this meant that the increase in internal energy directly matched the heat transferred to the gas. That was this case right here. However, when the gas was heated at a constant pressure, the increase in internal energy is supplemented. So this increase here is supplemented by the work that's done by the gas. And the total amount, right, equals the heat transferred, right? So we're not having to, it's not the same as the heat that's transferred. It's going to be, we will have to require less energy to heat something at a constant pressure. State the equation that relates thermal energy transferring to solids to its mass, specific heat, and a change in temperature. Well, that would be Q equals mc delta T, where Q is the thermal energy transferred by heat, that is in joules. M is the mass in kilograms. C is the specific heat capacity in units of joules per kilogram degrees C. This is in degrees Celsius, mind you. And delta T is the change in temperature in degrees Celsius. The specific heat capacity relates to how a specific material can change its temperature 1 gram of its material or 1 kilogram of its material by 1 degree Celsius. Thermal equilibrium is when there is no more transfer of energy, a transfer of thermal energy between the system. There's going to be no heat transfer because there's no difference in temperature. Use the specific heat of steel at 450 joules per kilogram degree C and water 4,186 joules per kilogram degree C to answer this question. If a 1 kilogram block is heated to 1 degree C and immersed in 1 kilogram of water initially at 20 degrees C, will their final equilibrium be closer to 100 or closer to 20? Well, let's see how we would actually calculate this, final equilibrium temperature, and let's see. Okay, now let's make sense of this calculation. First, let's start by the idea of conservation of energy here. The heat lost by the hot metal when you put it in water is gained by that water. So negative heat lost by the metal is equal to positive gain heat by the water. And I'm going to change the Q into MC delta T for the steel and MC delta T for the water. Notice it's negative MC delta T for the steel and positive MC delta T for the water. The next thing I'm going to do is I'm going to change the delta T's into the final equilibrium temperature minus the initial temperature it was at. So the equilibrium temperature T minus the initial temperature of the steel at 100, and then the equilibrium temperature of the water minus the 20 degrees C it started with. Then what I'm going to do is I'm going to distribute negative MSCS to both terms, and then MWCW to both terms. And then when I rearrange the equation and get the mass of water on one side and get the temperatures, I want to basically get the temperatures together. So I want to add MSCST over to the right and subtract 20 MWCW back to the left. And then, of course, when I factor out the common temperature, and then I'm going to be dividing by the sum of the MSCS, MWCW in the middle, I end up with this equation right here, or 100 times the mass of steel times the specific heat of steel plus 20 times the mass of water times specific heat of water divided by mass of steel, specific heat of steel plus mass of water, specific heat of water. And that's what I'm plugging into right here. 100 times 1 times 450 plus 20 times 1 times 4,186, all divided by, and that would be 128,720 over 1 times 450 plus 1 times 4,186, that would be 4,636. Dividing that, we get 27.7 as an equilibrium temperature. Therefore, through that long calculation, the equilibrium temperature is closer to the water. Section 12.5, applying the first law of thermodynamics to gas processes. A tennis ball moves in the positive x direction towards a smart tennis player. The tennis player causes the ball to strike the tennis racket while the racket is in the negative x direction, as shown in the diagram. Explain why every tennis player in the universe would do this. Well, the purpose of hitting a tennis ball with a racket is to return the ball to your opponent. So by reversing the direction of the racket opposite the direction of the ball, you will then be able to reverse the momentum of the ball and send it back to your opponent. A tennis ball moving in the negative x direction towards a moronic tennis player, the tennis player causes the ball to strike the tennis racket while the racket moves in the positive x direction, as shown in the diagram right here. Explain why this is the stupidest thing ever imagined in human history. Okay, maybe that's an exaggeration. But anyway, moving your tennis racket in the same direction of the ball is counterproductive to returning the ball and getting it back to the opponent. You lose out on the opportunity to send the ball back. Well, here's how this works. This is an analogy created to take a look at the gas particles against a piston compressing a gas or the piston expanding. As a gas gets hotter, temperature increases. When a piston pushes against to compress a gas, which tennis player, smart or moronic, is this like? Well, this is like the smartest tennis player that moves the racket towards the ball before collision. As the gas gets colder, temperature decreases. When a piston is pushed to expand the gas, or maybe the molecules push the piston themselves to expand the gas, which causes the gas temperature to decrease. Well, that would be like the dumb player moving the tennis racket, not bracket. That should be racket. Away from the ball. What is an isothermal process? Well, an isothermal process is one that occurs at a constant temperature. Now, using ideal gas law, since pressure times volume is proportional to temperature and temperature is constant, that means the product of pressure times volume is constant. So as pressure goes up, volume must go down by the same amount. And a pressure volume diagram would much look like this. State 1 here, state 2 here, and it would follow a curve looking something like that. Now, since pressure is directly related to temperature and temperature is constant, that means the pressure let me see. The pressure could increase. So the pressure increases, the volume increases, but the temperature remains constant. So we would have a temperature constant. We would have the temperature, the pressures at state 1. The pressure would move to state 2, but it would be at a constant temperature in that process. And then volume would be exactly the opposite. If pressure's decreasing, volume would be increasing. So volume would start down here. The state would increase the volume to a greater volume, maintaining the same temperature. What is an isochoric process? Well, that's a process that occurs at a constant volume. So again, looking at ideal gas law, PV is proportional to T. If volume is constant, that means that pressure increases with temperature. Now, in a pressure volume diagram, you would draw this as state 1 here, state 2 there, and isovolumetric or isochoric would just be a vertical line on a PV diagram. Now, in a PT diagram, if volume is constant, pressure increases with temperature. So if pressure starts down here and temperature goes up with pressure, that means you'd expect a constant increase. Since the volume was constant, with increasing temperature, you'd expect the volume to stay constant all the way across, even though the temperature increased from state 1 to state 2. Isobaric is a process that occurs under constant pressure. Pressure times volume is proportional to T. Constant pressure, that means volume increases with temperature. On a pressure volume diagram, state 1, state 2, isobaric process would be a horizontal line all the way across, increasing the volume at constant pressure. Well, the pressure is constant with increasing temperature, therefore a PT diagram would look exactly the same. A VT diagram, however, would be different because you're starting, if you have increasing volume, you have increasing temperature. Volume goes up with temperature. Like that. And an adiabatic process is one in which results in no energy transferred through heat. Q is 0. On a PV diagram, that would be a really steep curve like that. A scuba tank is filled with air that is compressed so that pressure is 100 atmospheres. When the valve is open, the air in the tank expands to the surrounding room. Released one way, the air expands adiabatically and the tank gets noticeably cold. Released another way, the air expands isothermally and the tank doesn't appear to change the temperature. Well, as was stated, the two ways the air can be released is isothermally and adiabatically. We are going to skip this section here. We're going to skip the crush the can demo. Section 12.6, changing state. It takes thermal energy to change the phase from solid to liquid, liquid to gas, or vice versa. What is the equation that relates the thermal energy input to or removed from a system in order to change its state? Explain the symbols. Okay, so when we're changing a state, okay, we need a certain amount of internal energy to make that happen, a certain amount of heat transferred, thermal energy happen. Well, basically, M times L is the equation, where M is the mass and L is the latent heat. That is the heat that is essentially keeping a molecule in its form, whatever form it is, gas, liquid, solid. And there's a certain amount of heat needed to, let's say, take something that's in solid form and allow it to change into liquid. And there's a certain amount of heat that's required to allow a liquid to be removed, a molecule to be removed from a liquid and go into a gas form. And consequently, going the opposite way, condensing, there's a certain amount of heat needed to condense the vapors of a gas together to make a liquid. And there's a certain amount of heat of fusion required to take molecules of a liquid and fuse them together to make a solid. So LF is the latent heat of fusion and LV is the latent heat of vaporization. But ML is our basic equation. Conduction is the process in which thermal energy is transferred through physical contact. When thermal energy is transferred through heating and physical contact, conduction, the high energy particles of the system bump into the particles that make up the wall of the container, thus increasing the energy of the particles of the container. Therefore, the container increases its temperature as well. What is the equation for the rate at which thermal energy is transferred? Well, the equation is H conduction, or you could write it Q over delta T, is equal to Ka delta T over L. Well, delta T is the change in temperature, not time. Okay, so let's break this down, sorry. So Q is the heat transferred. Delta T here is the time. So when we talk about the rate involves time. K is called the thermal conductivity. That depends on the material and how well heat transfers through that material. It could be like a pane of glass or a wall or some material, a door, material that makes up a door. Every material has its own measure of how heat transfers through it. Well, you also have A, which is the cross-sectional area in square meters. You also have delta T, which is the change in temperature. Now, what change in temperature means, it's the temperature on one side of the material compared to the other side. So if we're talking about a door, the temperature inside the door versus the temperature outside the door. Explain how a thermos bottle works. Well, if you can see in the picture here, a thermos bottle has a vacuum created between the inner wall and the outer wall. So basically, air is sucked out to create almost a perfect vacuum between the walls of the container. Now that works really well because a vacuum is the best insulator possible, since there is no air in a vacuum. And since there's no air between the two walls, then heat has a really difficult time transferring in or out of the inner container wall. Therefore, hot things stay hot, cold things stay cold. Let's take a look at this example. A large typical window pane glass having an area of 1 square meter. Suppose a glass of window pane thickness 5 millimeters has a thermal conductivity of 0.84 joules per second meter degrees C. Inside the house is 25 degrees and outside is freezing, 0. Determine the rate at which heat is lost through the window from inside the house. So we would list our thermal conductivity K at 0.84. The area is 1 square meter. The L is your thickness, the length or the distance of the window pane. 5 millimeters, but we got to change that to 0.005 meters. Delta T is 25 because that's the difference between 25 inside and 0 outside. Multiplying 0.84 times 1 times 25, take that and divide that by 0.005, and the rate, 4,200 joules of heat per second are lost through that window. Doesn't sound like a very efficient window. Now consider the electrical cost of 38 cents per kilowatt hour. Well, the units for this are also 4,200 watts. A watt is a joule per second. So what we can do is we can take that H, which is actually the power, right? 4,200 joules per second is 4,200 watts, and we can change that into 4.2 kilowatts by moving the decimal 3 times to the left. Now, if power equals energy times time, and energy, according to this, would be power times time, we could take the power of 4.2 kilowatts times the 1 hour, okay, and we get 4.2 kilowatt hours of energy. Now, if we take that energy and multiply it times the rate of 13.8 cents per kilowatt hour, that's $0.138 per kilowatt hour. You can see kilowatt hours cancels. Multiplying those two, you can see it costs about 58 cents every hour. Doesn't sound like a lot, but you keep adding up the hours, the dollars do add up. Explain how evaporative cooling works. Evaporative cooling works when a liquid evaporates from a surface. For example, when sweating in a dry environment as opposed to a more humid environment, you do not condense as much water in the skin as is evaporated. Therefore, water evaporated from the skin creates a net cooling effect. Convection is the heating process whereby the energy transferred by a fluid is moving vertically upwards. So if you think about it, the hot air rises above cold air. It's going to rise until it reaches the roof or ceiling or some limitation. Then that air is going to start spreading and moving laterally, and then it will start to cool down. And as it cools down, it's going to drop to lower, and the whole process creates what's called a circulation. Radiation, it represents the energy that all objects, hot or cool, give off. This energy is something that can pass through a vacuum.